we're going to wrap up with a nice physics-defying story out of our local favorite, UCLA. We literally can almost not go through 1 week without the UC system being one of our stories. This week it was two of our stories.
That's right.
Start with UCSD. This story is about new tech that's making our telescopes see things that really shouldn't be possible.
Yeah.
And this is out of the Astrophysical Journal Letters. I'm super excited about this story.
Yeah, this is a pretty crazy story. It's out of the UCLA Astrophysics department, along with a bunch of other institutions. What they've done is hack the telescope and have sharper views into the universe. Okay, and they hacked it to the point where even I was like, whoa. Okay, they have a line that I'll get to in their paper that I was like, what are you talking about? Okay, so the goal is always higher angular resolution. You want to be able to resolve smaller and smaller things. The epitome of that is the Event Horizon Telescope, which gave us that beautiful view of the black hole at the center of our Milky Way and the black hole in M86, which is a far, far away galaxy. You're looking at a thing that's about the size of a solar system, maybe several solar systems, but it's millions of light years away, right? It's insane.
It's not close.
It's not close. It's something like, I think somebody was saying something like the head of a pin, or they're resolving a quarter on the Empire State Building if you're looking from Los Angeles, right? Resolution is what that means.
Yeah.
How fine detail can you resolve something in the night sky? And we want to always push this as far as possible.
Right.
This is new work that came out of the UCLA Astrophysics department. What they've done is demonstrate sub-diffraction limited astronomical measurement. Okay? And that key thing is what got me, sub-diffraction limited. So what does that mean? Okay, there is a limit when it comes to the resolution that you can have with light. Okay? It's dependent on the wavelength and it's dependent on the size of your aperture.
Okay.
It's called the Rayleigh limit. If you've got 2 points of light that are really close together, as they are on the right-hand side,
Yes.
then they're going to look like 1 point of light, and I won't be able to resolve them differently. On the other hand, if I have 2 points that are a little bit farther apart, then I can resolve them because they're Gaussian peaks, this sort of like envelope of stuff.
Yes.
It's not technically Gaussian. It's like this other function called the Airy function. But in any case, if they don't overlap enough, I can resolve the two as separate things. Right?
Yes.
How far apart they need to be in angle, it's not actually distance, right? Because if something's closer, then they need to be closer away. If they're farther away, then they could be really far. It's the angle that matters. It's like the angle between them, right?
Yes.
And how far away they can be in terms of angle is determined by something called the Rayleigh criterion, which is what we just saw. It's a ratio between the wavelength and the diameter, okay? Wavelength divided by diameter times some constant, which has to do with the shape of your aperture. Usually it's 1.22 because your apertures are usually round. So the bigger the wavelength, the larger this angle has to be.
Right.
And that makes sense, right? Because if the wavelength is really large, then, we've looked at large waves that try to go across a rock.
Yes.
They get unbothered.
Yes.
Because the large waves will just go through.
right.
The smaller waves are the ones that'll bend.
Yes.
And that bending is what actually gives us any type of information.
Yes.
Also, the larger the diameter of your lens, the smaller you can resolve.
Yes.
Right? That makes sense. That's why we have big telescopes.
That's why I have these giant, massive telescopes. Big mirrors and lenses.
Yeah. One of the reasons is light gathering, but the other reason is so that we can have a giant sort of diffraction thingy that lets us resolve.
Yes.
Okay?
Yes.
And the one that they're doing here, they're using the 8.2 meter Subaru telescope in Hawaii. That thing, if we take the wavelength of light to be around 656 nanometers, the diffraction limit there with the 8.2 meter Subaru telescope is 20 milliarcseconds. Okay. And to think about arcseconds, it's like you got degrees. From degrees, then you get minutes. From minutes, you get seconds. And then from seconds is divided into 1,000 arcseconds. So it goes 60, 60, then 1,000. Okay, it's extremely small. It means if we were to look at Pluto right now from the Earth, Pluto would be a fifth the size of that angle. So Subaru telescope could actually tell Pluto and Charon apart.
Oh, yeah.
The Pluto and its moon apart, right?
That's
because its resolution is smaller than Pluto's.
That's quite
Right?
nice.
Pluto's about 100 arcseconds, and this thing's resolution is 20 milliarcseconds. 0.2 times 100, right?
Yep.
It's a fifth of that.
Yep.
Okay. There's a bunch of problems, right? The other problem that gets to us is not just Rayleigh thing, which is just physics.
Yeah.
Right?
Yeah.
Like even the Hubble has this problem. James Webb has this problem.
Yeah.
The other thing is we're under the Earth's atmosphere, and the Earth's atmosphere causes the twinkling of stars. It also causes the twinkling of distant lights if you're on top of a mountain, right? Because all the Earth's atmosphere has this turbulent packets of warm air and then cold air and highly dense and then lower dense. So the light is gonna start moving around before it gets to your detector,
Interacting with the atmosphere on its way to the whatever you're capturing it with.
Yeah, exactly. And so the resulting disk of your point source, let's say if you're trying to look at a star, it's going to go up by 500 to 1,000 milliarcseconds, right? It's going to be 25 to 50 times worse than that theoretical limit. Okay. And so what we can do is we can do something called adaptive optics. We can correct by making a fake star. Here, what you're seeing is the Keck telescope, and there's two lasers pointing out at where the telescope is looking, and it's creating a fake star there. The trick is the following. You've got a fake star that looks like any other star, but we know that it came from our laser, so it should be stationary.
Right.
The star and the stuff that I'm looking at could be moving and it could have dynamics.
Right.
But I know that the laser that I'm pointing is definitely straight.
Right.
Right. And the laser is going through the same bit of atmosphere that the starlight is coming in. So if I can change, if I have some kind of deformable mirror, right, that is taking that starlight, and right in the middle, I have like little ways in which I can change the shape of that mirror in order to keep that laser stationary. That's going to cancel out the effects of that column of the atmosphere.
Makes total sense.
Right?
I have to say this because I would be remiss if we didn't. We're in between photos 6 and 7 on the show notes.
Yeah.
And you literally... Anyway.
And I literally did it. Oh, God. But I still don't understand that. But
the point you're saying is because we have a fixed point from the lasers in the sky that we can then measure and basically remove the impacts of the atmosphere on how we're detecting the other stars because we have a fixed point that we control.
Yes.
That then can remove the noise that comes from the atmosphere.
Exactly. And then we can finally get to that diffraction limit.
Got it.
Okay?
Yes.
We can finally get to what the telescope is truly capable of given Rayleigh criterion. And here what we're seeing is the center of our Milky Way in infrared. On the left is without adaptive optics, and on the right is with adaptive optics.
My goodness.
You can see the huge change. This is how Andrea Ghez won the Nobel Prize.
This is crazy. For listeners who are not watching the video, and I encourage you to go to YouTube because we always have graphics for this. On the left, it basically looks like a gradient, a red-orange gradient.
With blobs.
It's just a massive
and maybe
blob.
20 blobs.
There's no discrete shape of any kind. It's just like a sauce.
Yeah.
On the right, you can see very discrete points of light, multiple. There's maybe...
Even in the zoomed-in version, right? There's an inset.
Yeah, there's
and
an
you can
inset
see in the inset, there's like...
It's incredibly high fidelity comparatively.
Yeah. And here, when you're looking at something called Sagittarius A star, and the stars around that compact object. And if we were to make a movie out of this, you'd see all of the stars going around an invisible point. Right? And that invisible point is our supermassive black hole.
Yep.
And this is why Andrea Ghez at UCLA won the Nobel Prize. UCLA has had an incredible history of imaging techniques. Okay, they're really good. They've got like 2 floors dedicated in the Knudsen Hall, I think, to just getting imaging to the next level. And this is the next sort of
LA
thing that they're doing.
Is the home of Hollywood, so
it is, right? Yeah. So that's pretty funny. So you can see now, right? Adaptive optics is insane.
Yes, that's a big deal.
The other thing that we can do is not just adaptive optics. We can make the telescope size bigger without actually making the telescope bigger. The effective size. You've seen this. The VLA. You've been to the VLA.
Yeah.
Very large array. Yeah, very large array in New Mexico. A giant 27-mile long radio telescope made of smaller telescopes that are all coordinated, and they can sense the time in which the light came. They can have them interfere. And so the light gathering power is not as much. You're not gathering as much light, but you're resolution is limited by how far away your telescopes are, right?
Yeah.
Now with radio, it's easier to do because the radio waves are slower.
Yes.
With visible light, it's harder, but actually the gold standard right now is in Mount Wilson. It's called a CHARA array. It's a six 1 meter telescopes all along the mountain that you can see over there.
Yes.
The baseline is 330 meters, so about 3 football fields wide.
Yes.
It's effectively a visible optical light telescope that is 3 football fields wide. And with that, you can achieve an angular resolution of 0.2 microarcseconds, which is insane because you can now image other stars like this.
Jesus.
Like this is a star called Altair. It revolves really fast on its axis, which is why it's got this like really big grapefruit bulge on the equator because it's revolving so fast. And because in the equator you can also see that it's dimmer.
Yeah.
Because like that gas is farther away from the equator compared to the pole.
Yep.
So it's a little bit dimmer. Right?
Crazy.
This is a single star that we're imaging like this.
Yeah, that's incredible.
It's incredible.
No, it's
We've
incredible.
also with the CHARA array, we've been able to see sunspots on other stars. So star spots on other stars with the CHARA array. And it was really cool because the last time I went up there was for one of these, they have classical music concerts at Mount Wilson in the telescope dome.
Interesting.
And I, for the longest time, thought that nighttime astronomy was dead at Mount Wilson because of the light pollution from Los Angeles. Nighttime astronomy had been retired and all they did was solar astronomy. But no, CHARA was up there, 6 small 1 meter telescopes all along the mountain. They route their light through vacuum tubes.
Which is crazy.
And then they have a central array where they make them interfere and actually get that resolution. It was cool. Yeah,
That's really cool.
Astronomy, cutting edge astronomy is still alive and well in Mount Wilson.
In beautiful sunny Los Angeles.
Los Angeles, where it all started. So this paper's profound claim. So we've gone through, Rayleigh limit, which is just the physics of light waves.
Yes.
And we've gone through the atmosphere and so on and so forth.
Yes.
The core claim that got me thinking about with this paper was they said the Rayleigh criterion is not fundamental. So it's like Jack Sparrow being like, it's more like guidelines, right? Like not like I was like, what are you talking about?
Right,
I thought the Rayleigh criterion, I learned this in undergrad and I thought that was it.
Yeah, right.
Insane. So here's the thing.
The idea is like previously this was viewed as a fundamental limitation at a physics level.
At a physics level, right? Then I started reading. So the Rayleigh criterion assumes the following. The only thing that you're sensitive to is the intensity of the light. Okay? Mm-hmm. You've got a telescope, you've got a CCD in the back. The telescope creates an image. The CCD then tells how much intensity of light is coming from this direction, and it creates an image. Okay? But light is an electromagnetic wave, and there is phase information.
Okay.
Right? Because the electromagnetic wave is coming at you. At some point, it's going to be up. At some point, it's going to be down this way. Right? There's a phase. There's a timing that the light is coming through. And if you can extract the timing, then you have both parts of the wave. You have the amplitude, which is the intensity, which you already had. And you also have the timing in which that wave packet came in. Right? And so now, it's kind of like with a complex number, right? A complex number, as I said the other day, it's a clock that has a length and it has a phase. We were only sensitive to the length of this thing with the CCD. What these guys are doing now is they're getting sensitive to the phase of that light, creating much more information out of that single resolution.
Out of the existing system that's already there.
Yes.
Which is like a key
idea. They're adding another little piece of equipment.
Right.
Instead of the CCD, they have this thing that we're going to talk about. But that thing is now going to capture all of this additional information. And what's happening is they're dividing up the light into its notes. Into its musical notes. Like when you listen to a musical note, let's say a chord that has A, C, and a G. That's 3 different piano keys that are put down, right? How does your ear hear it? Your ear actually hears the 3 different notes. The way it's doing it is there's hardware inside of our ear that's in the cochlea. The cochlea is this curled up little thing. That's a hardware part of our ear. And what it does is it's made out of cells of different thickness, okay? The lower frequency, the bass notes, are going to vibrate the cells with the big thickness. and the higher frequency are going to vibrate the thinner, smaller cells. So where in this spiral the cells are getting excited tells you which piano notes are being played. Okay? Our ear has hardware that is breaking down the sound that is coming in into its respective modes, as you would say, into its respective like components. Okay? We're going to do the same thing with the light that's coming through a telescope. Okay? Yeah. What we have is we've got a waveguide that takes in the light that's coming in from the telescope.
Yes.
Okay? And then what it's going to do is make it go through this fiber optic sort of chassis.
Okay.
And all of that multimodal, the sound that's coming from an instrument is going to be broken down into these modes.
Yes.
Into each individual fiber optic cable.
Yes.
Okay? And so you're decomposing the light field into a basis of what are the notes that make up that light field.
Which also changes over time.
Yes. And each of those notes has a certain phase to it, right? Yeah. Because some of the notes are going to be arriving a little bit later, some of them earlier, some of them are going to be louder than the others. And so if you go to the next one, we'll have, this is what the light notes look like. On the left-hand side over here, we've got the actual image. Let's say it's a dot with a ring around it or something like that.
Yes.
That can be broken up into a dot in the center.
Yes.
Then there's maybe two lobes this way. There's two lobes this way.
Yeah.
And what we can do is we can say, what are the modes, which are these individual notes? How do they add up to make the image that I'm seeing? That's what that deconstruction is doing.
You know what this looks like for any video or film editors that are listening? It looks like the color panel on DaVinci Resolve when you're color correcting your video footage. It gives you the color wheels of all these different permutations. It literally looks just like it. It's actually
it's kind of similar in that sense, right? It's like it's extracting this like low information, right? All the stuff that makes it up. This is only really possible if you look at very simple objects, for example, a single star, or like stuff around a single star. If you wanted to, image the Eagle Nebula or something, this wouldn't really work.
That's fair.
But the mathematics is simple because the source is simple.
That makes
sense. Because the source is simple, I only need to worry about the first like 20 notes.
I got you.
I don't need to worry about, because you can, in theory, you can recreate any image using like just a bunch of like notes like this.
Yes.
But in practice, it's going to get difficult.
That makes sense.
With a simple objective, which is just, we're looking at a star. We want to resolve the stuff in the star and around the star very, very nicely. That's what we can do. And the key principle is the phase information of that input is now converted into a measurable intensity difference between all of these different notes, right?
Yes.
If the star's position, for example, it shifts, then one of those fiber optic inputs is going to be brighter than the other. If it shifts the other way, then another fiber optic input is going to be brighter, right?
Yes.
And the raw data has gone from being a CCD to now it's not a picture of the star, but it's 38 different spectra, 30 in each of these different modes. Okay? So it's like how loud was this note at this frequency?
Yes. So to speak.
So to speak, right? Yes. This is but that's the best way that I can describe it.
We're trying to distill it into an analogy that doesn't require us to go through more.
Go through all of the data, but it's like they've basically got 19 different notes and 2 polarizations, because polarization is also important, right? Yes. The electric field oscillating this way or this way tells us something about what the thing is that is producing that light. So it's 19 different nodes, all in 2 different polarizations to get 38 different spectra.
The idea is, before we were looking at just like one box, and now we have like 19 boxes with 2 flavors to analyze the same object we were looking at before that was just one box.
Yes, exactly. And the one box, sure, it had the direct information of how bright this thing was, but now we're just sophisticating it, right? We're no longer taking, let's say, just how loud the sound is, but what are the thingies on top?
The another analogy this makes me think of is like for DJs, when you get a track, right? The track is like one audio waveform, and it has the drums, it has the vocals, it has everything as one waveform.
Exactly.
Now there's all these AI tools that allow you to separate out the drums from the vocals, from the synths, and now you have it as these and like there is information when you're looking at just the individual instrument that is hard to decipher when you're looking at the single waveform.
Yeah. And this is very similar to that.
I think
I think that's a good analogy, right? It's taking the aggregate light,
Yeah.
and it's decomposing it into these
individual
modes.
Yeah. Yep.
You know.
Yep.
And what you can do now, the second thing that you can do is this star. It's got two different. So this star specifically, what they're looking at is a star in Canis Minoris, Beta CMI. It's 162 light years away. It's surrounded by a gas of hydrogen. Canis Minoris is one of the two dogs that are the hunting companions of Orion, the hunter. And so this star specifically, it's got a gas of hydrogen around it, and that gas is spinning so fast that we can see a Doppler shift, where on one side it's blue shifted because it's coming at us, and on the other side it's red shifted because it's going away, right? So what we want to do is resolve this gas cloud, okay? There's two ways to do this. There's two steps. The first is to say, okay, all of the light, most of the light is coming from the star, right?
Yeah.
There's going to be some jitter because of the adaptive optics.
Yes.
Remember when we talked about the episode about AI being used for LIGO, for the gravitational observatory?
Yes.
And I told you that when you have these control systems, you can eliminate low frequency noise,
Yes.
but you're going to inject high frequency noise,
Yes.
right? This thing is injecting high frequency noise,
Got
right?
it.
So that there's going to be some jitter of the star there, right? What you can do is you can capture that response map of a single star that's basically telling you how the instrument and this modal system that we have is responding to that jitter at every single point that the star is at. Okay? So you've got a response map effectively being like, this is what the astronomical jitter from the star is.
Yes. Yes.
That's from all of the light.
Yes.
Then what you do is you look at something called the H alpha emission line. Okay? The H alpha emission line is because of quantum mechanics. Hydrogen has discrete levels.
Yes.
Right? And whenever the hydrogen atom goes from the n equals 3 to n equals 2 energy, it releases this red light that's right at 650 nanometers, about. So I think 656 nanometers, okay? So if we look only at that frequency of light, we're going to see the gas cloud, the accretion, the disk.
Yes,
of hydrogen around
disk,
the
the star.
So what we can do is we can take an image in the H alpha line.
Yes.
We can take an image with all the light, subtract the two, and we'll get a nice hydrogen gas cloud
that is surrounding the star. And so it's like not just that. Okay, we're now able to basically make the star's structure and the gas cloud structure discrete.
Yeah.
Using this methodology.
Yes, exactly. And we can do it because this is sub-diffraction, right?
Right.
This is where we're going way inside what Rayleigh even thought was possible.
Yes. Okay.
Right?
Yes. That tracks.
It's pretty cool. And what they found is with this technique, they found that the disc was lopsided.
Okay.
It's not completely like a plate. It's not symmetric. There's like a little bulge to it that they actually saw. And there's a non-zero shift in that accretion disk, and that means that now the modelers can go and be like, okay, how do we get something like this, right?
What is causing that non-zero shift?
Exactly. Yeah, I mean, I think it's really cool. It proves that you've got this compact. It's cost effective. You just like stick it in the back of the telescope, right where the light was coming in. Now it goes through this other thing.
It's a bolt-on. It's like a bolt-on.
Yeah,
like you don't have to rebuild any of these systems from scratch. You can add this as an add-on. And it just receives the existing feed and then processes it.
Yeah, and then processes it in its own way. And there's so much more that we can do with this. You can put this on a space telescope, for example, because those guys are also limited by Rayleigh, but maybe not anymore. And the last photo that we had, photo 19, I just wanted to dwell on a little bit. There you can see the gas cloud and you can see the clear Doppler red-blue shift, right? Between the part that's coming away from us and the part that's coming towards us. The blue is where it's coming from towards us, and the red is where it's going away. And that scale bar is 1 micro arc second, right? And I told you before that it used to be 20. Now you've resolved stuff to that.
To 1.
Right?
And you can even see the lopsidedness that you were talking about earlier in this too. Yeah. This is unbelievable.
So I think it's a new dawn of higher than Rayleigh resolution.
Yeah. Which is, I
think it's going to be really, really cool.
Again, this is where we talk about this all the time. There's a compounding happening right now of these fundamental either techniques, methodologies, tools, combination of these things that are now not only allowing us to take our existing tooling and make it better, take our existing data sets and analyze it differently, but giving us a totally new way in which we see the world around us. This was a good story.
I think it's really cool.
No, this is really cool.